RIK 113 is located approximately 431 light-years away in the southern sky, nestled within the constellation of Scorpius. Also catalogued as 2-mass J6EM 6683010-270, this distant star may seem like just another point of light to the naked eye. But behind it lies a young, dynamic system that offers an exceptional window into the early stages of planetary formation. What makes RIK 113 particularly fascinating is its structured protoplanetary disk, a dense, swirling region of gas and dust that serves as the raw material for the birth of planets. These disks are common around young stars, but the one encircling RIK 113 stands out due to its intriguing complexity. The journey to uncover the secrets of RIK 113 began when astronomers first studied it, using the powerful Atacama Large Millimeter, Submillimeter Array, or ALMA. ALMA's highly sensitive radio antennas, located high in the Chilean Andes, are designed to detect the faint signals from dust and gas in space. It was through this instrument that scientists began to piece together the disk's remarkable features. The data revealed the presence of a large, dark gap within the disk, a void that hinted at the possible existence of a forming planet carving its way through the cloud. Such gaps are strong indicators of planetary formation, as young planets tend to scoop up or disturb the surrounding material while they orbit their host star. Inspired by this tantalizing clue, researchers decided to take a closer look using another state-of-the-art facility, the Very Large Telescope, VLT, operated by the European Southern Observatory. Located in the Chilean desert, the VLT offers some of the clearest views of the night sky and is equipped with a specialized instrument called SPHERE. SPHERE is particularly adept at imaging exoplanets and the dusty disks around young stars. It can filter out the bright light of a star, allowing astronomers to observe the faint structures nearby with incredible clarity. When scientists turned SPHERE toward RIK 113, they discovered something remarkable. The new images revealed that the inner ring of the disk wasn't just a simple band of dust. It contained delicate spiral arms, twisting elegantly around the star. These spirals are significant because they are exactly the kind of structures predicted by theoretical models of planet formation. According to simulations, as a planet forms within a disk, its gravitational influence distorts the surrounding material, creating wave-like patterns, spirals, that radiate outward. To find both rings and spiral arms in a single system, and in such a precise arrangement, was a rare and valuable find. Dr. Christian Ginsky from the University of Galway, one of the leading astronomers in the study, explained the significance of the discovery. Although his team has examined nearly 100 protoplanetary disks over the years, RIK 113 stood out as something special. It's uncommon to find a system where all the textbook features, rings, gaps, spirals, appear so clearly and in such harmony with theoretical expectations. It's as if the system were putting on a performance just for astronomers, demonstrating the subtle mechanics of planetary birth. But the surprises didn't end there. A deeper analysis of the VLT data revealed not just one, but two potential planetary signals, signs of emerging protoplanets embedded within the disk. These hints were found near the location of the original ALMA detected gap, lending more credibility to the idea that this is not just random turbulence or shadow play within the disk. While the current evidence is suggestive rather than definitive, the consistency between two separate observations, from both ALMA and the VLT, strengthens the case for at least one, and possibly two, nascent planets orbiting RIK 113. The astronomers were able to map the disk's structure in great detail. The inner portion extends out to around 40 astronomical units, AU, that's about the same distance as Pluto is from our Sun, and is decorated with two graceful spiral arms. Beyond this, separated by a wide gap, lies an outer ring that stretches all the way out to 115 AU. This is an enormous region by solar system standards, and provides a vast arena for planetary formation to take place. By comparing their findings with computer models and simulations, researchers estimated that the potential planet shaping these structures could be a gas giant with a mass somewhere between 1/10 and 5 times that of Jupiter, depending on which model is applied. One of the intriguing aspects of the RIK 113 disk is how different it is from others, such as the well-known PDS-70 system. In most similar systems, the spiral arms either lie outside the ring or aren't clearly visible. But in RIK 113, they are located inside a scattered light gap and ring, an unusual and telling configuration. This unique morphology could be due to variations in the disk's viscosity, a property that influences how gas and dust flow and interact within the disk. A higher viscosity could explain why the spiral arms are more pronounced and why they occupy this particular location. The implications of this discovery are far-reaching. If the presence of one or more planets in RIK 113 is confirmed, this system could become a cornerstone in the study of how planets interact with the disks they form from. Such interactions play a critical role in determining the eventual structure of planetary systems, including factors like planet size, orbit, and even the presence of moons or rings. In many ways, studying systems like RIK 113 allows astronomers to rewind the cosmic clock and witness the processes that shaped our own solar system billions of years ago. Observations like these also contribute to the broader quest to understand the diversity of planetary systems across the galaxy. As telescopes become more advanced and data analysis more sophisticated, we are finding that no two systems are exactly alike. Some, like our solar system, end up with neatly spaced rocky and gas giant planets. Others form with hot Jupiters orbiting close to their stars, or with icy super-Earths in distant eccentric orbits. By examining systems at various stages of development, such as RIK 113, scientists are building a cosmic family album of planetary formation. One that helps explain not just where we come from, but where we might find life elsewhere in the universe. Another exciting aspect of the RIK 113 discovery is the promise it holds for future investigations. Instruments like the upcoming Extremely Large Telescope, ELT, also being developed by the European Southern Observatory, will offer even higher resolution and sensitivity. These tools could confirm the presence of planets around RIK 113, measure their masses and compositions, and even begin to analyze their atmospheres. With such detailed information, we could begin to distinguish whether these planets resemble Jupiter, Saturn, or perhaps something altogether new. There is also the potential to observe changes in the disk over time. Planetary formation is a dynamic process that unfolds over millions of years. While we can't watch entire solar systems evolve in real time, careful monitoring of systems like RIK 113 over years or decades may reveal subtle shifts in the positions of the disk AS structures, confirming the influence of unseen planetary companions. This kind of observational time-lapse would be like watching an embryo slowly develop into a child, one stunning frame at a time. In a universe filled with trillions of stars, each potentially hosting its own planets, RIK 113 is a reminder of how rare and precious these detailed snapshots of formation truly are. It's easy to overlook the distant pinpricks of light that make up the night sky, but each of them might be nurturing planets, moons, and perhaps life. With each new discovery, our sense of cosmic perspective grows, and the line between science fiction and scientific fact becomes increasingly blurred. As for RIK 113, the research is still ongoing. Astronomers will continue to monitor the system with various instruments, each unveiling new layers of complexity. And as they do, they inch closer to answering some of humanity's oldest questions. How did our world come to be? Are we alone in the universe? And what other wonders are waiting to be discovered just beyond the reach of our current tools? In the coming years, we can expect more revelations from systems like RIK 113. The technology is catching up to our curiosity, and with that, our understanding of the cosmos is entering a new golden age. What was once invisible is now in focus. What was once theoretical is now observable. And what was once a mystery may soon become knowledge. All thanks to stars like RIK 113, distant beacons that, through the language of light and gravity, tell the story of creation itself.